Hess's law. So Hess's law says that if a reaction is carried out in a series of steps, the delta H for the reaction will be equal to the sum of the enthalpy changes for the individual steps of the reaction. So here's what that's about. Let's say I want to go from San Francisco to Denver. So here's San Francisco down here at sea level. So that's San Francisco. All right. So it's at 0 feet. And Denver is up here at 5,280 feet. We call it the Mile High City. But I got a terrible travel agent who sends me up to land in my airplane on the top of Mount McKinley at 10,000 feet, and then down to Dallas, and down at Dallas, let's say that's at 500 feet, and then finally from Dallas to Denver. So if I were to add up the changes in altitude, so if I went from 0 to 10,000 feet, that's a plus 10,000 feet. And I apologize for the handwriting in this particular case. Then I went down to 500 feet for Dallas. That's a minus 9,500 feet. And then finally I went up to Denver, and you have to forgive me, that's 5,280 feet minus 500, and that's 4,780 feet. So that's a plus 4,780 feet. So look at what I've done. I've gone up, then I've gone down, and then I've gone back up. Well, if I add all of these things up, 10,000 plus a minus 9,500 plus 4,780 feet, I come up with 5,280 feet, which is simply the difference between San Francisco's altitude of 0 feet, because it's right there at sea level, and the 5,280 feet. State functions. Delta H is a state function. Altitude is a state function. They only depend on the final state and the initial state. So Hess's law says that if I know the delta H for a series of reactions, that I can add them up to get to what we call my target reaction. And this can all work because enthalpy is a state function. So let's take a look at an enthalpy problem. So I'm going to go ahead and I'm going to bring this up as a Word document so I can write in here. Again, I need to get a pen, and we'll go ahead and, well, let's see, we're in black. Let's go ahead and keep it red this time so that I can write on the blue and have you actually see it. So there's certain features of Hess's law problems. This is my target reaction. This is my target. This is the goal of, and I don't know what the delta H for this reaction is. The delta H is a mystery to me. However, I can go to a series of reactions that I think might get me there. This is like my travel agent giving me the different pathways to this reaction, and so this is my route to get to that reaction, and I can manipulate that route. And using the laws that we've learned about the properties of enthalpy and the delta H, I can manipulate these path reactions to add up to my targeted reaction. So the first thing I always look for is there a reaction I need to reverse or flip? And so the keys to doing that are to find features of the path reactions that match up with features of the goal reaction. So here I see SO2 as a product in my target reaction, but I see SO2 as a reactant in my path reaction. So if it's a reactant here and it's a product in my target reaction, I actually need to flip this reaction because SO2 is a reactant here and it's a product here. So I'm going to go ahead and reverse that reaction, and that's going to give me 2SO3 decomposes into 2SO2 plus O2. Now, if I've reversed the reaction, remember the delta H for the forward reaction, or sorry, for the delta H for the reverse reaction is equal in magnitude but opposite in sign. So my new delta H will have the same magnitude, but instead of being minus 196, it's going to be plus 196 kilojoules. Okay, so now here's my second reaction. And in my second reaction, I'm looking at it, and sulfur is definitely a reactant in my path reaction. It's also a reactant in my goal reaction. So I think that, and SO3, if I notice this is a product in this reaction, and it's not in my target reaction at all. So I actually want SO3 to cancel. So if SO3 is a product in this reaction, looking at my reverse reaction here, SO3 is a reactant here, that SO3 is going to cancel. So I'm just going to transfer this reaction down here as 2 sulfurs plus 3 O2s is going to give me 2 SO3s. So when I do that, I see that the delta H for my reaction is still minus 790 kilojoules. Minus 790 kilojoules. So now my next step is to see if there's anything I can cancel. Well, I see that I've got SO3 as a reactant in my first path reaction and SO3 as a product in my second path reaction, and it's just like adding up algebraic equations. If I have the same term on opposite sides of the equal sign, I can go ahead and cancel that term. So I can cancel the SO3 from the reaction. Now I can simply add everything up. And so if I add this up, I get 2 sulfurs plus, and I'm looking at, I've got 3 O2s here and 1 O2s here. So I can go ahead and I can cancel 1 of the O2s. That's going to give me 2 O2s instead of 3 O2s. So now I'm going to have 2 diatomic oxygens, and that's going to give me my product of 2 SO2. Now, I want to go ahead and add up the delta H's for my 2 reactions, and when I add up my delta H's, I have 196 positive plus a minus 790, and that's going to give me a minus 594. So that gives me a delta H so far that equals a minus 594, and that's an equal sign right there, kilojoules. Now, the question I have to ask is this my target reaction yet? And I notice that no, the coefficients in my target reaction are all 1. So this is not my target reaction yet. I need to divide everything by a factor of 2. And if I'm going to divide all of the reactants and the products by 2, I have to divide the delta H by 2. So once I do that, let me go ahead and get this down. Once I do that, I have sulfur plus O2 gives me SO2. And if I look once again at my target reaction, I have sulfur plus O2 gives me SO2. So these path reactions have added up. They've added up to give me my target reaction. That tells me that since my delta H is just another product of this reaction, that dividing that by 2, the minus 594 by 2, will give me the delta H for this reaction. And the delta H for this reaction, having used Hess's law, is equal to minus 297 kilojoules. That's my delta H for that Hess's law problem. Let's try another one. Let's go to this one, which is a little bit more complicated. This is my, let's get a pen so I can write something. Pen. And same color, same thickness. Okay, so we're good. Okay, so we're ready to go. Here's my target reaction. This is my goal. What I'm going to try and do, using Hess's law, is to get all of these path reactions to add up to my target or goal reaction. That's my goal reaction. Okay, so the first thing that I want to do is I want to see, is there anything that I need to flip? Is there any reaction that I should reverse? Okay, well, the first reaction I'm looking, and I see HF right here. HF is a product in this path reaction. HF is a product in the goal reaction. So I believe I should leave this reaction as is. Down here I'm looking at CF4. It's a product in this path reaction. CF4 is a product in my goal reaction. So I'm going to leave this reaction as is. I'm not going to reverse it. Now, I look at this reaction on the bottom here and I see C2H4. And C2H4 is a product in the path reaction, but it's a reactant in my goal reaction. So what I think I need to do is reverse or flip this reaction. So I'm going to flip this bottom reaction. So I'm going to go ahead and reverse this reaction. I'm going to rewrite, well, before we rewrite, let's see if there's anything else we need to do. Let's go back to the HF. I look at the HF and I have two HFs in my path reaction here. I have four HFs in this reaction. Since I need four HFs, what I can do is I can multiply all the coefficients in this reaction by 2. And 2 times 2 will give me 4 of these. Well, what you have to remember is that the delta H is also a product of this reaction. So if you multiply the reactants and the products by 2, you also have to multiply the delta H by 2. We'll take a look at this second reaction. I've got carbon tetrafluoride, and I have carbon tetrafluoride as a product in this reaction. And the coefficient in my target reaction is 2. The coefficient in my path reaction is 1. So again, I need to multiply all the coefficients of this reaction by 2. And if I multiply the coefficients of all the reactants and products by 2, I have to multiply the delta H by 2 as well. So I'm going to rewrite everything. And this might take a little bit of time, so that gives me 2H2 plus 2F2 gives me 4HF. And since I multiplied my minus 537 by 2, I need to go ahead and multiply that by 2 as well. 2 times a minus 537 gives me minus 10, looks like 1,074. So I now have a delta H that's equal minus 1,074. Over here, what have I got? I've multiplied everything by 2, so I need to multiply my delta H by 2 as well. So that's going to be 2 times minus 680, which gives me a minus 1,360. So let's go ahead and write the reaction first. So that's 2 times carbon plus 4 F2s, and that's going to give me 2 CF4s and a delta H that's equal to minus 1360. Okay. Finally, I'm flipping this reaction. I don't have to multiply it by anything, but that's going to give me C2H4 decomposes to form 2 carbons plus 2 H2s. And if I've flipped the reaction, I have to change the sign on the delta H. So the sign on the delta H is now minus 52.3 kilojoules. So the first thing I want to do after I've gotten that all squared away is I need to see if I can cancel anything. First thing I notice is I have 2 carbons on the reactant side of this reaction and 2 carbons on the product side of this reaction. So I can go ahead and cancel these 2 carbons. It's just like canceling 2 components that are identical on each side of the equal signs in an algebraic equation. I also notice that I have 2 hydrogens that are products in this reaction and 2 hydrogens that are reactants in this reaction, so I can cancel those. I think I'm ready to add things up and see if I get my target reaction. So I only have one of these C2H4s. That gives me C2H4, and I have 2 F2s plus 4 F2s, which gives me 6 F2s. And in case you're wondering, the reason I'm not canceling the F2s is because they're on the same side of the reaction arrow. They're both reactants, so they just get added up. And now I have 2 CF4s, and I have 4 HFs. What I want to do now is I want to compare. Let me fix that. So didn't like that at all. Okay, go back, get a pen. And now I've got 4 HFs. I want to compare this reaction to my target reaction. So my target reaction is C2H4 plus 6F2 gives me 2 CF4s plus 4 HFs. And if I go back down, that's identical to the reaction that I got. So all I have to do is add up the delta H for each of my path reactions, and I'll get the delta H for my target reaction. And I'm going to go ahead and do that. That gives me, let's see, that's minus 1074 plus a minus 1360 plus a minus 52.3. And that gives me a total, a grand total, of a delta H of minus 2486 kilojoules. And that is the delta H for this reaction based on Hess's law. And the reason this works is because enthalpy is a state function. I can get the delta H for this path reaction by simply adding up the delta H's of all of these path reactions. I have to do a little manipulation. Again, the first thing I do is I look for a reaction that I might have to flip. You may not have to flip a reaction, but often you do. So look for that. And then if I need to multiply one of my path reactions to get the number, in this case, of HFs to match the target reaction, I multiply by that factor. In this case, it was 2. Don't forget that if you multiply a reaction by 2, you multiply the delta H by 2. You do the same thing to the delta H that you did to the path reaction. Cancel what you can, add everything up, and if it equals your target reaction, just add up your delta H's, and there you go.